So we're going to spend the next part of the class discussing things that happen in solution. A solution is a homogeneous mixture of at least two different substances. And because it is a homogeneous mixture, it's uniform down to the molecular level, such that the ratio between the components is pretty consistent. And when we deal with solutions, usually traditionally when we think of a solution, we think of liquids, but there are many other types of solutions. Air is a solution of oxygen and nitrogen. Metals can form solutions with other metals. Brass is a good example of this. So it's a homogeneous mixture of two or more substances. Traditionally, we have a tendency to think of it as a solute, some component that is dissolved in a solvent. So, for instance, this bubbly beverage, the solvent would be water, and the solute would be the sugar and carbon dioxide. So we have a gas dissolved in a liquid, and we have a solid dissolved in a liquid. Both of those would be solutes in this solvent of water. And we have a tendency to think of aqueous solutions as those that deal with water as the solvent. And that's where we'll spend most of our time, is in an aqueous solution. So, let's talk about the behavior of things in solution. We spent all this time talking about ionic compounds, and when those materials dissolve in water, they don't stay discrete. If you take sodium chloride and you plunk it down into water, what will happen is the sodium ion will dissociate from the chloride ion. They'll separate. And so when sodium chloride as a solid is dropped down into water, you end up with separate sodium ions and chloride ions. These materials are what we call electrolytes. Materials that dissociate in water. Usually they're charged species that dissociate into separate pieces. Now, the reason for this has to do with the structure. The water molecules will interact in specialized ways with the individual ions, muting the attraction between them and allowing them to be separated from one another. They'll actually stay pretty close together in solution, but they are physically separated. These are what we call electrolytes. What that means is, though, that certain materials will release more ions into solution. If you take this magnesium chloride and you dissolve it down into solution, Mg plus 2, Cl minus, we can see that the magnesium chloride will release twice as many chlorine ions as the sodium chloride. And so we can vary the amount of chlorine and based upon the types of salts that we place into solution. So to differentiate sodium dissolved in something as opposed to liquid sodium, which would mean something very different, we define this as an aqueous solution, AQ for the state. And the assumption is that this really also represents a mixture of sodium ions, aqueous, and chloride ions, aqueous. When something dissolves in something else, we say that it is soluble. And solubility, how soluble something is actually a continuum. Sometimes some things are very soluble. That means that you put a large amount. Sometimes they're insoluble. That is, almost none of the material goes in. In reality, usually a small amount of material dissolves in water. Anybody ever drink out of a garden hose? You put a little garden hose, or you take a summer swig. It tastes kind of funny sometimes. Well, that's not because your hose is dissolving, but small quantities of it are soluble in the water, or leave a trace quantity. So usually we draw the line as if something is noticeably soluble, we place a macroscopic quantity into water and it dissolves. Salt in water is said to be soluble. So we represent that with the little aqueous, but in reality we have to take into account that it really is separate ions that are dissociated. Now, there are electrolytes. So we have our electrolytes, and there are also materials that are non-electrolytes. They do not dissociate in water. Sugars, when you dissolve them in water, they are also aqueous, but they remain as discrete entities. They do not dissociate any further. And how do you tell the difference? Well, usually an ionic compound will be an electrolyte, and a non-ionic compound will be a non-electrolyte. Typically. Not always, but typically. And of course, there's a range, and there are some materials that are weak electrolytes, which means that they have partial dissociation, and we'll cover those more next semester. But for now, we just have to concern ourselves with electrolytes and non-electrolytes. Why do we bother with solutions at all? Well, there's a couple reasons. There's a couple benefits to solutions. One of the major benefits for dealing with solution is that they are homogeneous. And so it allows for very rapid mixing of components. Solid-solid reactions are notoriously slow. And so, but in solution, we can make things go much faster. We can bring things into contact much more readily. So solutions have that benefit of rapid mixing and faster reactions. On top of that, solutions also have a nice tendency to have better thermal control, particularly aqueous solutions. So many reactions give off lots of heat, and so if we do things in solution, we can avoid negative side effects from a large amount of heat being released. The water is able to absorb that heat quite readily. So good thermal control. And another benefit of solutions is precision. You can get a much higher degree of measurement. For instance, most analytical balances in the lab, they're only good out to about a milligram, maybe a tenth of a milligram. And so you can't really weigh anything smaller than a milligram. So how do you weigh a microgram or deliver a microgram of material? Well, if you take a milligram and you drop it down into a liter of solution, you now have a milligram in a liter, and then you take a milliliter of that solution, and you now have a microgram of material that you can then deliver. And so it allows you to measure much smaller quantities by taking advantage of the fact that they are homogeneous mixtures. Additionally, so we're going to look at 3 common chemical reactions that take place in solution. The first are precipitation reactions. Precipitation reactions where we will take two aqueous solutions and mix them together, and a solid will form in solution, precipitating out. That solid is what we call the precipitate, leaving a few leftover ions in the solution. So that's the first style of reaction that we're going to look at, precipitation. We'll also be looking at those in lab. The next style of reaction are acid and base reactions. Acid and base reactions involve something, typically with a proton, reacting with something else, not always, but typically with an OH minus, to form water, and usually some sort of salt. These are proton exchange reactions, where the proton migrates from one location to another. Now, we can also see acid and base reactions that take place in the absence of water formation, which is also quite common. Again, these are also proton transfer reactions. So acid-base reactions usually involve, directly or indirectly, a proton transfer, H+ transfer. And these are, again, one of the fundamental reactions we'll see in solution. Usually acid-base reactions involve mixing an acid and a base. We've already looked at a big pile of acids in our naming, so we have a huge arsenal to work with. We haven't really talked about bases, but many of them are metal hydroxides. And lastly, we're going to look at redox reactions. Redox reactions involve, rather than proton transfer, electron transfer. Some species that's transferring electrons between a component, and you end up with an electron transfer that takes place, making one thing a little more positive and another thing a little more negative. These are electron transfer reactions. We will touch on electron transfer reactions this semester, but we'll delve more heavily into them in the second semester. Proton transfer, we'll look at it, the most basic style of proton transfer, called the neutralization. And our goal is to be able to spot each of these different types of reaction. Each of these different types of reaction just by examining basic chemical reactions, and maybe even predict.